Hello folks, and welcome to this lesson on hybridization. By the end of this lesson, you should be able to explain how hybridization is a part of bond formation and predict the geometry around an atom from its hybridization and vice versa. So throughout the lessons, learning about the orbitals and shapes of them, and then learning about VSEPR shapes, and also when you were learning about the sigma bonds and pi bonds, you might have been questioning, or you might have been asking yourself, well, how do all of these things all relate to each other? Because you have these VSEPR shapes where you have your central atom and then you have your terminal atoms, and these shapes are always consistent depending on how many of these electron domains you have, but each of these individual atoms are going to have s orbitals which look like that, p orbitals that look sort of like that, d orbitals where some of them look something like that, and you have all these different shapes. And then you have sigma bonds and pi bonds, so how does this all fit together? Well, this all fits together because of hybridization. So yes, when you have an individual atom, it has its s orbitals, p orbitals, d orbitals, and so on, and they all have those individual shapes. But whenever you're forming covalent bonds with other molecules, what happens is that you combine a certain atom's atomic orbitals from that valence shell, you combine them all together, and then from that you separate them into a special set of directional orbitals. So it's basically as if you take all of the different shapes that you need and that are going to be forming this bond, pretend it's Play-Doh, clump it into one big ball of Play-Doh, and then you separate them into different shapes that are equal to each other. And then you use those special shapes to make the different bonds that you have. So when you're doing the hybridization itself, you are going to combine as many orbitals as you need. So you'll always be using that s orbital, you use as many p orbitals as you need, and if you need even more than that, so when you're going into those 5 electron domain, 6 electron domain shapes, then you also bring in those d orbitals as well. If you're going up to the 4 electron domains, you're only going to be using those s, p, and d, s and those 3 p orbitals. Now, when a question is asking you about the hybridization of this, of a certain thing in a question, it's always referring to a specific atom in a molecule. It's not talking about the hybridization of the whole molecule. It'll be specifically an atom in that molecule itself. So if we're dealing with an atom, a molecule that has one central atom and then terminal atoms, typically the hybridization is going to refer to that central atom, though I can ask about the terminal ones as well. And if you have a bigger structure where you have a chain or a ring or something like that, when it's asking for the hybridization, it's going to ask for the hybridization of this specific carbon or that specific nitrogen or so on and so forth. Now, an exception to all this hybridization stuff is going to be hydrogen, because hydrogen only has one valence electron, which is in that first shell, which only has one s orbital. So there's nothing to hybridize when you only have that one shell, so hydrogen doesn't undergo hybridization, but everything else will. So, if we're going to go back to that lesson on sigma and pi bonds, how does this all fit into the hybridization thing? Well, your sigma bonds are made from hybridized orbitals. So hybridization happens, and then when you get a bond forming from that, the sigma bonds are from hybridization. Also included in the whole hybridization thing are those lone pairs as well. However, pi bonds are overlapped p orbitals. So the p orbitals themselves stay as they are. They're not part of the hybridization. You just take those p orbitals and then you overlap them. So how does this all work? Well, let's take CH2O as an example. So if we're going to take CH2O, we're going to draw out that structure, and then you want to know what the hybridization around that carbon is. Well, this carbon is going to have, there's a sigma bond there, there's a sigma bond here, and there's also a sigma bond there. There are no lone pairs, so we don't have to worry about that in terms of the carbon itself, but we do know that there is a pi bond between that carbon and that oxygen as well. That's that second bond between the carbon and the oxygen. So carbon has 3 sigma bonds in this case. So if you have 3 sigma bonds, you need 3 orbitals to combine to then be hybridized. So in terms of the hybridization, you need 3 orbitals worth because you have 3 sigma bonds. So that's going to be an S, and then your remaining 2 are going to be both P's. So you need an S and 2 P's, and so the hybridization of that carbon is going to be sp2. Now in this particular molecule, you can also ask about what's the hybridization of that oxygen. Well, in this case, you see that you have 2 lone pairs. You're going to have a sigma bond with that carbon, and then the last bond is going to be a pi bond, so that doesn't count towards hybridization. So the hybridization for the oxygen, you need 3 again, so that's going to be S and 2 P's. So this oxygen also is going to have a hybridization of sp2. So I'd like you to pause the video, draw out these structures, and see if you can find out the hybridization for each of these atoms. Alright, so here are each of these structures drawn out. Remember, we don't have to worry about hybridization for hydrogen, so we only need to talk about the nitrogen for this first one. With this nitrogen, you can see that there is 1 lone pair, and then you have 3 sigma bonds, so that's 4 of these orbitals that need to hybridize. So we're going to have sp3 hybridization in this case. Now, both of these carbons are going to have the same hybridization because this is perfectly symmetrical. So if we take a look at this carbon, you're going to see that there is 1 sigma bond here, there's 1 sigma bond here, and then 2 pi bonds there. So that means that there are 2 sigma bonds worth of hybridization that you need to do. So you're going to take an s orbital and a p orbital, hybridize those 2, and that's the hybridization around that carbon. And again, because they're perfectly symmetrical, you get the same hybridization for that carbon as well. Hydrogens we're not going to worry about. For this oxygen, you have 2 sigma bonds, the bonds with the hydrogens, and then you have 2 lone pairs, so that's 4 orbitals worth of hybridization that you need to do. And so this is going to be sp3 as well. Now, if you're finding the idea of counting how many sigma bonds and lone pairs there are to figure out your hybridization, another way that you can look at this is look at how many electron domains are around that particular atom. Because when you do that, if you take a look at your nitrogen here, there are 4 electron domains. You can see that there are 4 orbitals worth that you needed to hybridize. In this case, you have 2 electron domains, same idea, and so on and so forth. So use whichever method works better for you. That's the end of this lesson. I'll see you next time.